Alright, let's talk about continuity of functions when it comes to calculus. At this point in our math careers, most of us have already come across this vocabulary word before, and we've been told that if you can trace a function without having to pick up your pen or pencil, then that function is continuous. Now, this definition is still true, and it's still a good way to kind of get a feel visually if a function has continuity or not. But now we're in calculus. So let's revisit this idea of continuity using what we've learned about limits. So our new definition of continuity begins with the phrase, a function is continuous at a point A if the limit as x approaches a of the function f of x is equal to the value f of a. In other words, the limit as x approaches a from the left must equal the limit of f of x as x approaches a from the right, which must equal the value f of a. So in a way, we're going to go through 3 checkpoints when looking to see if a function is continuous at a given value. Does the limit as we approach a from the left equal the limit as we approach a from the right? And is the actual value at that point also equal to the limit values at that point? If your answer is yes to all 3 of those questions, then we know that we have a continuous function at that point. So what are some ways our graph may not meet these requirements? Well, we're going to look at the definition and think of what might happen. So with discontinuities, there's 2 major groups. The first group we're going to look at is removable discontinuities. So when I say that a discontinuity is removable, basically what I'm saying is that it's possible for us to fix it and somehow make the graph continuous again. And so the only type that we can consider removable would be a hole, right? Because we can literally fill in a hole with a value so that it's not a hole anymore, and then our graph would magically be continuous again. And the reason that a hole is a removable discontinuity is because the part of our definition that says that the limit has to equal the value at that point won't hold true if there's a hole. So basically it's a hole because f of a is undefined. So it doesn't really meet that checklist, or that specific check on our checklist for continuity. So the second type of discontinuity is called non-removable. So non-removable discontinuities are basically anything that's not a hole that'll cause some sort of problem with our definition. So these are things that we can't just fill in one value and then the graph is magically continuous again. So there's 2 types you're going to come across that are non-removable, and those are jump discontinuities and infinite discontinuities, which are basically vertical asymptotes. Okay, so with jump discontinuities, that's when you have your graph doing something and then it breaks and then continues again from there. So it has some sort of gap or space where it's literally jumping to the next part of the function. And with these, the part of the definition of continuity that won't work is that our left-hand and right-hand limits equal each other. A lot of times the actual value at the function will equal one of the limits, but it can't equal both because they approach 2 different numbers. Alright, so it's that part of the definition. Let's look back. This part right here isn't working for us with jump discontinuity. Okay, so with infinite discontinuity, that's when we have some sort of vertical asymptote occurring. Okay, and with these we actually have a lot of problems. So not only is our left hand and right hand limits not approaching the same value, we actually don't have a value defined if there's a vertical asymptote at an x value on a graph. So in fact, none of our definition of continuity works with that type of infinite discontinuity. However, if you're answering a question on a quiz or a test, all you have to say is that it's a non-removable. It's very rare for them to ask you also, is it then jump or infinite? Although you should feel pretty comfortable differentiating between the two at this point. Okay, so back to this. Left and right hand limits don't match. And f of a is also undefined. So it's got all the problems. Okay, but it really doesn't matter. If just one part doesn't work from the definition, that's all that has to happen for it to be considered discontinuous. So one more side note on the definition of continuity. A lot of times in these problems in calculus, you'll hear them use the phrase it's continuous on a given interval, or maybe it'll also say sometimes on its domain. Okay, so watch out for this, but also it's kind of helpful. Okay, so a function is continuous on an interval, right? That's the little phrase we're looking at. If it is continuous at every number on that interval. I know that seems like an obvious explanation, but so a lot of times a function is continuous everywhere on its domain, and that's kind of like a sneaky way of saying hey, there might be some discontinuities in the domain, but everywhere there's not a discontinuity, it's still continuous. So, okay, what am I talking about? So some functions that we should kind of know from this point going forward that are continuous everywhere on their domains. There's a couple. The first one that we come across a lot are polynomials. So x squared, x cubed, x to the 100th power, whatever power it may be. Polynomial functions, if we're just thinking of a quick sketch here, are the ones that just, we've got our cubic or we've got our quadratic. Okay, and they all basically match one of those two forms based on if they're odd or even. But everywhere on that function, there's a continuous graph. There's no vertical asymptotes, holes, or jump discontinuities. So if you see that a function is a polynomial, then you know that it's continuous everywhere on its domain. So another common function we have a lot in this class are rational functions, right? So that's usually when we have polynomials, but they're written as a numerator and a denominator. So for those, they're continuous everywhere except where their domain is not. So for instance, if you had a vertical asymptote at 2, okay, your rational function looks like this. So what this phrase is saying is that it's continuous everywhere on its domain, because when you write the domain of a rational function, you take out the x value where there's a vertical asymptote or potentially a hole, so that it is continuous on its domain. Another common one is the root function, right? Radicals, square root x, things like that. And these functions have a natural restriction to their domain because we can't take square roots of negatives. So what you have to keep in mind with any radical function is, let's say we had this under the radical. Okay, anything underneath here has to be greater than or equal to 0. If it's something that's in a rational function, like in the denominator, then not only does it have to be equal to 0, or sorry, that was wrong. Not only does it have to be greater than 0, it also can't be equal to 0 if it's in the denominator. So there's a bunch of things to watch out for just with the domain of this function. But once you've defined the domain of this function, we know from that point on that it is always continuous after that. The last common type you might see is a trig function. We know that they oscillate in both directions, and so there's no asymptotes or holes for us to worry about. They're continuous from left to right. So one type of function we do a lot with that is not part of this group that's continuous on its domain are piecewise functions. Because anytime you see a piecewise function, right, a lot of times it includes all parts of the domain, right? So maybe something like that. So it's saying that it is including all x values here, but you have to check and make sure, I'm just making this up so it's not super helpful, but you have to check and make sure that there's not something that would cause a problem. So for instance, this one is including a 0, yet I could not plug 0 into that function. That's part of the piecewise. So just be aware that piecewise do not have this lovely feature of being continuous on their domain, that you have to still check each piece before figuring out that answer.